Have you ever stopped and wondered how your phone, your laptop, or even your smart fridge actually thinks? Well, it all boils down to a secret language, a simple conversation happening in ones and zeros. Today, we're going to pull back that curtain and look at the most fundamental building blocks of all digital tech, logic gates. So here's the big question. How does a machine, something that only understands on or off, make a decision? How can it possibly add numbers or play a video or just register a simple mouse click? It seems impossibly complicated, right? But the answer is actually surprisingly simple. You know, the best way to get your head around this is to think of logic gates as digital Legos. Seriously, you start with just a handful of very basic, super simple bricks. Each one has just one simple rule. But when you start snapping them together, you can build literally anything, from a tiny calculator all the way to the most powerful supercomputers on Earth. Okay, so let's get into it. Let's meet our three most fundamental bricks. These are the absolute core pieces that almost everything else is built from, and their names are and, or, and not. First up is the AND gate. This one is the strict one, the bouncer at the club. It will only give you a true output. That's a 1 if every single one of its inputs is also a 1. It's like a high-security lock, right? You need the key and the password to get in. One without the other just isn't going to work. And this little chart, this is called a truth table, and it shows you the rule perfectly. You've got your inputs, A and B, over on the left. Now just look at that output column, Y. The only time we get a 1 is on that very last line, where A is 1 and B is 1. See? Simple. In the language of circuit design, this is written as Y equals A dot B. Okay, next up is the OR gate. Now this one is way more laid back than the AND gate. It'll give you a 1 output if input A is 1, or if input B is 1, or hey, even if both are 1. It's much, much easier to get a true result out of this one. And what's really cool is seeing the difference. Check out its truth table. As long as there's at least one 1 somewhere in the input rows, you get a 1 as the output. The only way to get a 0 is if both inputs are 0. Its expression is Y equals A plus B, which totally makes sense since it's so much more inclusive. And our third primary brick is the NOT gate. Now, this one looks like the simplest of all, but don't let that fool you. It is incredibly powerful. It only has one input, and it has only one job, to do the exact opposite of whatever you give it. It's an inverter. I mean, the truth table couldn't be any clearer, right? If a 0 goes in, a 1 comes out. If a 1 goes in, a 0 comes out. That's it. Its expression is Y equals not A, and you'll often see it written with a little bar over the letter. Okay, so we've got our three main bricks. Now, what happens when we start snapping them together? Well, we can create new, more powerful Lego pieces. And these next two, they're called universal for a very, very good reason. Say hello to the NAND gate. And the name tells you exactly what it is. It's a not AND gate. You literally take the output of a regular AND gate, and then you just run it through a NOT gate to flip the result. And if you compare this truth table to the AND gates we saw a second ago, you'll see the output column is the perfect opposite. Remember how the AND gate had 3 zeros and then a 1? Well, the NAND gate has 3 1s and then a 0. A perfect inversion. And following that exact same logic, we have the NOR gate. You can probably guess this one, right? It's a NOT OR gate. You take the result from a standard OR gate and, yep, you flip it with a NOT gate. And once again, this truth table is the direct inverse of the OR gate. The only time a NOR gate ever outputs a 1 is when both of its inputs are 0. So here's the crucial point. These combo gates are called universal because you can actually build any other type of logic gate, and, or, not, you name it, using only NAND gates or only NOR gates. Now think about that from a manufacturing standpoint. It's incredibly efficient. Instead of needing different setups for different gates, you can just mass produce one type of brick and build everything from that. It's cheaper, simpler, and it really makes them the ultimate digital Legos. All right, so besides the primary and universal gates, we also have some specialist bricks that are designed for very specific jobs. Let's take a look at the most common one, the XOR gate. The name here is the real key, exclusively OR. This gate's a little bit picky. It gives you a true output only if one input is true or the other is true. But, and this is the important part, not both. The inputs have to be different from each other. And you can see this rule perfectly in its truth table. When the inputs are different, a 0 and a 1, or a 1 and a 0, the output is 1. But check out that last line. when both inputs are 1. Unlike a regular OR gate that would give you a 1, the XOR gate gives you a 0. Exclusively one or the other. So we have our bricks. We know their rules. Now for the really fun part, snapping them together to build something that actually does the calculation. Let's just walk through a really simple circuit. Okay, let's trace the signal. We've got 3 inputs. A is 1, B is 0, and C is 1. So in step 1, A and B go into an AND gate. And since 1 and 0 is 0, the output is 0. Easy enough. Then that 0 becomes an input for the next gate, along with C. So we have 0 or 1, which results in a final output of 1. And just like that, we made a complex decision. That little circuit is really just the beginning. When you scale this whole idea up, and I mean way, way up, that's how you get the incredible technology that powers our world. And this isn't just some abstract theory, you know? These gates are right at the heart of stuff you use every day. Think about a push-button lock on a door. It's basically a series of AND gates checking if you've pressed button 1, and button 3, and button 7. Only when all those conditions are true does it finally unlock. It's the exact same simple logic, just applied to a real-world problem. And the scale of it all, it's just mind-boggling. The only real limit to how many of these digital Legos you can cram into a device is the physical space on the silicon chip itself. Modern processors have not thousands, not millions, but billions of these microscopic gates, all working together in perfect harmony. So as you finish watching this, just take a second to think about it. Inside the very screen you are looking at right now, these simple rules, AND or NOT, are firing off billions of times every single second. It really makes you wonder, what other incredibly complex systems in our world are built from such beautifully simple beginnings?